So what we have in front of us right now is the truth table for AND gate, and what our model would look like with it. So over here we have a function n, or rather a neuron n, with input variables as x1 and x2, and the weights that we are assigning to x1 is w1 and x2 is w2. So with that, we also have the truth table. As we all know, the AND gate would only output a value as 1 in case both the inputs that we are providing are 1. If either of them is 0, it will give us the output as 0. So with this, let us see how it will work. So over here, we have an equation of what this output y, how this output y is, how we are going to get this output y. So for what this function will do is, it will take the input x1, multiply it with its weight w1, then it will add it to this x2 into its weight w2, and then add in this bias, which we use to make sure that our result is not differing just due to a constant value and not due to the weights. So with this, let us consider the first case in which we provide both inputs as 0. In which case, first let us assign weights. So we will consider W1 to be 10, and let us take W2 as 10 as well, as we need the appropriate weights to test if it is going to work. And then let us take the bias as -15. With this, let us test the first case. With input x1 as 0 and x2 as 0 as well, we want output for y. So when we input these two variables, what we get is something like this. Our x1 w1, which is 0 into 10, plus x2 w2, which is also 0 into 10, minus the bias 15. Now this gets us a value of sigmoid of -15. For now, that probability would be below 0.5. So we would be considering that as a 0. Then for the next case of 0 and 1, what we will have is x1 into w1, which is 0 into 10, and then 1 into 10, which will give us 10 over here, and then -15, which totals to sigmoid of -5. Again, this is a negative value. So the sigmoid lies below 0.5 in case of a negative input. So again, we will have 0 over here. This next case will be just similar to this, just we are switching the x1 and x2 over here. And this will also give us a 0. Now with the final equation, what we have is we are providing both x1 as 1 and x2 as 1 as well. So with that, we will get 1 into 10, 10 plus again 10, and then -15, which results in a +5. Now that is a positive value, so sigmoid would give us a value greater than 0.5. Now for that, we will take the output as a 1. So what is basically happening over here? What this neuron did is that it just used these weights and bias to establish a boundary. So if we plot these points, that is 0, 0, 0, 1, 1, 0, and 1, 1 on a graph, this is how it will look like. This green point over here is the only case in which an AND gate would result into a positive value, that is a value of 1. And other all three values resulting in a black dot are zeros. So what exactly did our model over here did? What exactly did the function over here did? So it basically established a boundary. It divided the 3 points in which either of the input variables was 0, and made two sections of it. With this, it separated the value where we had the output of the AND gate as 1. Now, this was just a simple AND gate, which was similar to a logistic regression. The only difference is that in that example, we didn't consider a small number of outputs. We just directly considered a whole image. Over here, we are just considering two input variables. Now, to make sure that we are getting this right, let's see another example with this. So over here, we will see the Xor gate. Now, this is how an Xor gate is usually made. This is how it will usually look in electronics. But how exactly would we implement that as a neural network? So we all know that the inputs of XOR gate are only one in case the inputs are not similar. That is, either of them is 0 or 1, and the other one is the different input. In case both the inputs are same, that is, both are 0 and or both are 1, the output that we get is a 0. So let us see how that works. So over here, we have a neural network. I hope it is visible to all of you. And I have already assigned weights and biases over here. Now, how I obtain these biases and weights is through trial and error. Like I have already trained a model, and from that I have taken these inputs. How you can take this is find out these inputs and place them over here is something that we'll see further into the session. For now, let us see how this implementation of XOR would work. For this, over here, we are providing inputs 0 or 1, depending on the case that we are studying. Over here, we are establishing the weights for each input. For example, if I am presenting an input from this, let us consider this to be an X1. If we are considering an input from this place into, okay, just let me write this on screen. So if this is our X1 and this is our X2, and we are taking an input from X1 to A, the weight is 1. From X2 to A, the weight is also 1. When we are considering the input X1 for the neuron B, we are taking in a weight of -1. And for the next one as well, we are taking in a -1. So we just saw the diagram of XOR gate over here. What we are trying to do now is implement this with the neural network. So I expect my first neuron A over here to work as an AND gate. And the equation for that would look something like this A over here. So what this is doing, the result A over here would be sigmoid of X1 into its weight W11, which is 1, plus, let's name it over here, W11. Then we will also have this one, which is W2, sorry, this is W12. This is W21, and this one is W22. Sorry for the bad handwriting. Then, just so that we are on the same page, this output A that we are getting over here would be the sigmoid of X1 into W1, its weight, that is 1. And the bias, that is 0.5, is something that we will subtract from the addition of these two, that is X1 W1 plus X2 W2, 1 minus the bias B. So what output is this giving us? In case both these inputs are 0, we will be multiplying them each with 1, which is 0 again, and then 0.5. So we will be getting as minus 0.5 as inside this over here. So a sigmoid of minus 0.5 would be a negative value. So we will assume that to be a 0. In case either of these is positive, what we would get over here is 1 plus, again, 1 into 0 would be 0, 1 minus this bias 0.5 over here, which would give us a plus 0.5 inside the sigmoid, resulting in a probability that we want is greater than 0.5. So we will take that output as a 1. Now, the only case remaining for this OR gate is that when both inputs are 1, we will be doing something like 1 plus 1 minus 0.5, which is 1.5. And then again, we will be getting a value positive. So the sigmoid would be greater than 0.5. And again, we will be resulting output would be 1. Now for the not AND gate, or rather the NAND gate, what we are taking in as weights are -1 and -1. So in case both the outputs are, both the inputs are 0, we will be passing in 0 over here, 0 plus 0 and minus of minus 1.5, which is plus 1.5, which would give us again a positive value over here. So in case both the inputs are 0, the resulting output would be 1, which is exactly what a NAND gate does. Now, in case only one of these inputs is 1 and the other is 0, we will see that case as well. So considering this input to be 1 and this input to be 0, what we will be getting is 1 into -1, that is -1, plus 0 into -1, that is 0, that is -1 plus 0 plus of 1.5, which would again be a positive 0.5. So the sigmoid would again give us a value greater than 0. Sorry, and that would be, sorry, the sigmoid would give us a value greater than 0.5. So we will consider that to be a 1. Now, the only case in which a NAND gate should give us a 0 output is when both these values are 1. Now, when we consider this as 1 and x2 as 1 as well, what we will be doing over here is -1 into 1 plus -1 into 1 minus of -1.5, which totals to -0.5. So the output of B would be sigmoid of -0.5. That would give us a value smaller than 0.5, which would be 0. Then for the AND gate, the final gate that we are using, coming from the diagram of XOR gate we saw, we are assigning weights as 1 and 1 in both cases. So in case the outputs over here are dissimilar, for example, it's 0 and 1 over here and 0 and 1 over here, we were getting outputs as 1 in both cases. So the AND gate would work something like 1 plus of 1 minus of 1.5, which is 0.5. We are getting a positive value, and that would provide us with an output greater than 0. And the case where both these values are the same, for example, over here both values are same, then this OR gate would result in a 1. However, this NAND gate would result in a 0. And as this is working as an AND gate, the output we will be getting for similar inputs would be 0. So what exactly this neural network did for us? Now in this neural network, we had two inputs over here, a hidden layer in here with two neurons, and one neural layer over here with one neuron. So what exactly did we do here? So what we did is we took in these input points. For the XOR gate, the only one output that we get is when the inputs are dissimilar. So for 0.1 and 1.0, we would be representing it with a 1. Let's take in the green color for that again. And for inputs, when both inputs are same, we will be getting a 0 value. So what exactly did our circuit over here did, our algorithm over here did? So the first OR gate that we used, or rather let us first see the NAND gate that we just referred to. Our NAND gate did something like this. It drew a line over here. Everything below this line, marked on the side with the arrow, is where we are getting a 1 input. This is what the NAND gate did for us. For our given inputs of 0, 0, 0, 1, 1, 0, and 1, 1, it separated the inputs where the NAND gate is getting an input of getting an output of 1, and then mark them as 1. Our OR gate did the opposite. For in the opposite direction, what the OR gate did is, for every value that it is getting as a 1, it placed it above its line. And the final AND gate that we have over here combined the region that these two lines are providing us, giving us this region between as the output. In this way, the XOR gate that we have over here used 3 perceptrons to work as an XOR gate. Now with this, I'll stop and hand over the session to Sanket.
Yeah, before moving on, let's just answer a few of the questions in the chat box, right? First of all, guys, don't get confused between all these terms, okay? We don't want you to have any preconception about what neural network is and what all have you heard before about neural network, let's say linear regression, whatever algorithms you have heard. We just want you to think about neural networks as a function, a simple function that takes some input, as Aditya said, and gives you some output. Okay, so Aditya, could you share the screen again?
Okay, sure.
Yeah, so first let's answer a few of the questions. So few of you have questions regarding why did we take bias and weights that we took for the given example. So this is the key. Okay, you're actually pointing towards the right question, because right now we just saw that this is an XOR, right? And if we put in our values and multiply it with the given weights also we call it weights because it is like a weighted mean, right? So at any point, let's say point A, right now we call it point A, it's called neuron actually, but we call it point A. So any point, it's taking input weighted average of the inputs, and what the weight should be is decided by us right now. And right now we Aditya has taken it as one, right? So how did he came up with it? Right now we just use trial and error. Okay, so but how we came up with the weights and the values of bias is the actual question which we will be answering throughout today's session. Okay, because that is what we call as training. Okay, right now you just saw a working neural network. What is a neural network? In the end, just a function. So you saw a working neural network, but how did these values came at the first place, right? So that's actually perfect question, and that's what we are going to answer throughout this today's session, right? So that's what was about weights and bias and how we came up with it. And as Aditya just said, each and every neuron or each and every point, which we call, right, for now we can call it a neuron, which it just decides a boundary, a decision boundary, right? And this decision boundary separates two classes, class 0 and class A or class B. And that way we have implemented an XOR gate.